Hello and welcome to 50 conceptual questions answer video series. So here is the second questions. So in this questions it has been written that a monochromatic laser beam is incident on a wet piece of filter paper out of a sheet of glass of thickness D. The pattern observed is on the paper is shown in the figure. If the radius of the inner ring observed is R, then the refractive index of the glass must be option A, option B, and option D. So try to understand what has been asked in this question. So let's say we have a glass plate. So this is our glass plate. And this glass plate has thickness D. And then they have put another piece of wet filter paper on the top of this glass plate. And after then laser is incident on the top of the glass plate. And when the laser is incident on the top of the glass plate, this pattern is observed on the paper. And look at this figure and try to understand the features of this pattern. So it is not a large number of concentric circle as it is formed like in uh, Newton rings and Febvre interferometry. It is just a single bright spot at the center, and then at a distance r, the intensity is maximum, and then intensity of this bright circle is reduced as the radius is increases. So now this question is, if this glass plate thickness is D and this circle radius of this inner circle is R, then what will be the refractive index of this glass plate in terms of R and D? So if we want to find out the refractive index of this glass plate in terms of R, that is radius of this circle, and D, the thickness of this glass plate, what will be that refractive index of this glass plate? So I hope what has been asked in this questions, it is clear to everyone. Let's try to understand how this pattern will form on the paper. So this pattern will form not because of like any kind of interference or as it form in Newton rings or Newton ring experiment or in Febvre interferometry. Here this pattern will be formed because of total internal reflections. So to understand that how this pattern will form because of total internal reflections, first we have to understand the concept of total internal reflection. Concept of total internal reflection. Concept of total internal reflection. Okay. So to understand this, let's say this is the interface of two medium. This is the interface of two medium, and this side medium have refractive index 2, and another side of the interface is radius medium have refractive index 1. So this is medium 1, this is medium 2, and let's say assume that n1 is greater than n2. That is refractive index of the first medium is greater than the refractive index of second medium. That's mean this second medium is actually rarer medium. Rarer medium, and since first medium have higher refractive index value compared to the second medium, so in this case first medium will behave like as a denser medium. Okay, denser medium. And then let's say this is the normal at the interface. So this is normal to the interface. Now if light is incident from this medium 1, that is from denser medium, let's say making an angle theta 1 with normal, and some amount of light will reflected back in this medium, and some amount of light will go to the second medium. And in the second medium, let's say let's make an angle with the normal theta 2. Okay, theta 2. Then according to Snell's law, Snell's law, we can write up n1 sine theta 1 is equals to n2 sine theta 2. N2 sine theta 2. Now if we take the ratio of this sine theta 1 and sine theta 2, we'll get n2 divided by n1, and already we have assumed that the medium 1 is denser medium and medium 2 is rarer medium, that is a refractive index of medium 1, that is n1 is greater than n2. So this ratio of n2 by n1 will be less than 1. So this should be less than 1. So that means this sine theta 1 will be less than sine theta 2, or we can say theta 1 will be less than theta 2. So what this suggests? This suggests that because of presence of second medium, the light will bend away from the normal in second medium. If there is no second medium, then light is supposed to go in this path. But because there is a second medium, so light will not follow this path. It will be bent away from the normal. That's why theta 2 will be always greater than theta 1 when light is incident from rarer medium to denser medium. So there may be a case that if we increase the incident angle, we keep on increase the incident angle, then maybe we'll get a case when let's say this is another angle, and for this angle, since angle in medium 1 theta 1 will be always less than in medium angle that will be make the light with the normal in medium 2, that's mean theta 2 will be always greater than theta 1. So there may be a case when this for a particular angle of in medium 1, the light will goes parallel to the interface of two medium. Parallel of the interface of the two medium. That's mean in the second medium, light will make a 90 degree with the interface. This particular angle of incidence is called critical angle. Particular angle is called theta c, that is called critical angle. So critical angle is an angle of incidence at which if light is incident on the interface of a medium from denser to two medium, from the denser medium, then reflected light goes parallel to the interface of two medium, that is reflected light make a 90 degree with the normal. And then if we still increase the refractive index, incident angle, and in this case if this incident angle is more than this critical angle, then what will happen? Then all the light will reflected in the first medium only. So there will be no transmitted light, all light will be reflected back in medium 1. medium 1. So this phenomena when light is incidence from denser medium to when light goes from rarer medium to denser medium at an angle greater than the critical angle, then light doesn't go to second medium and all light return back to the first medium from the interface of these two medium. Then this phenomena is called total internal reflection. This phenomena is called total internal reflection. But first we have to calculate what is the value of this critical angle. So what is the value of critical angle? Critical angle. So when light is incident at critical angle, the reflected light goes parallel to the interface. That's mean reflected light will make a 90 degree with the normal. So again, if we apply this Snell's law at this point, what we'll get? We'll get N1 sine theta c. N1 sine theta c is equals to N2 sine theta 2, but when light will incidence at the critical angle, so then theta 2 will be 90 degrees. So we'll write N2 into sine 90 degree. Sine 90 degree. And sine 90 degree is 1. So what we'll get? We'll get N1 sine theta c is equals to N2. N2. And from there we can write sine theta c, that is sine of critical angle, will be N2 by N1. Or if we want to write theta c, that is critical angle, theta c can be written as sine inverse N2 by N1. Sine inverse N2 by N1. So if we want to find out critical angle at any interface of two media, then how we can write? We can write simply sine inverse N2 by N1, where N2 is the refractive index of rarer medium and N1 is the refractive index of denser medium. That we have to remember. So the critical angle theta c is equals to sine inverse N2 by N1, where N2 is the refractive index of rarer medium, N1 is the refractive index of denser medium. Okay. And second thing that we have to remember that here, what are the conditions for this total internal reflection? Conditions for total internal reflection. Conditions for total internal reflection. Total internal reflection. Condition for total internal reflection. So total internal reflection takes place based on two conditions. First condition, that this figure we can see that when light which goes from actually denser medium to rarer medium, then only actually theta 2 will be greater than theta 1. You can solve this problem in another way. You can send a light from rarer medium to denser medium, and then you can also find out this theta 1 relations between theta 1 and theta 2. You will see you will get always theta 1 will be greater than theta 2. So that's mean if light is sent from the rarer medium to denser medium, in that case light will be bent towards the normal. So there we will not get never total internal reflection. So total internal reflections only take place when light will goes from denser medium to rarer medium. So here is the first condition, that the light must be traveling from traveling from a traveling from a denser medium to denser medium into a rarer medium. So this is the first condition for the total internal reflection. Light must be traveling from the denser medium into a rarer medium. And second condition, the angle of incidence the angle of incidence angle of incidence must be greater than the critical angle of the interface. The critical angle of the interface. Okay. So when these two conditions will satisfy, when light will goes from a denser medium into a rarer medium, and the angle of incidence must be greater than the critical angle of this interface, then only total internal reflection take place. Now when total internal will take place, all the light will coming back to the denser medium. Again, there will be no transmitted light in the rarer medium. So to solve this problem, we have to remember these two conditions, this concept that total internal reflection, concept of total internal reflections, and when these total internal reflections will take place, and what will be the value of critical angle of an interface of two media. Okay, then let's try to understand how this concept of total internal reflection will create this pattern that is given in the questions. Okay, then let me draw this 2D figure of this question that is given in the question. So let's say this is our glass plate. This is our glass plate of thickness D. Of thickness D. And then they have put thin piece of filter paper, wet filter paper, on the top of the glass plate. And after then, they have sent a laser light on the top of the glass plate. So what will happen when this laser light hit the filter paper? Since it's a wet filter paper, so first of all it will create a bright spot at this point, and then since there is a wet filter paper, so light will scatter from this position in different angle, and the scattered light will goes at different angle. Maybe some amount of light goes in this direction and then it will passes through the plate. Some amount of light scattered at different angle, it's this angle, and then other side also on the same angle like this. And then this is the, look at this line. So this is the interface of two media. What are these two media? One side is glass, another side is air. So let's assume that glass have a refractive index Nz, and air, other side is air, so air have a refractive index Na, and we all know that air refractive index is 1, and we have to find out this glass refractive index. So, and we also know that reflective index of glass will be always greater than the air. So that's mean in this case, this glass plate will behave like as a denser medium, and this air will behave like as a rarer medium. So when light will incident at this interface, scattered light will bend away from the normal. So it will goes in this direction. And similarly, this point also goes away from this direction. Okay, so the scattered light, if we consider another scattered light in such a way so that let's say this scattered light, and at this position, the angle of incidence, let's say if we make draw a normal to the interface, this is the normal to this interface, and this angle, this is called an angle of incidence at this point. So if this angle of incidence is greater than critical angle, then what will happen? Since here you can see that light is goes from the scatter light is goes from denser medium to rarer medium, and if this angle of incidence is greater than critical angle, then low light will transmitted in the air, all light will coming back to the glass again. And when this light will come back to the glass again, so it will follow this path and it will hit the glass plate here. And similar on the other side also we can make as diagram here. So light will goes in this direction, then this is the normal to the interface, normal to the interface, and if this angle is greater than critical angle, then no light will goes to the air, light will return to the glass plate and it will hit the glass plate, this it will hit the paper at this position. So you can see in this figure, when laser light will hit the top of the glass plate, there will be a bright spot, and then this region, in this region there will be no light because all the light will passes through this glass plate. And then when the incidence of on the bottom plate, bottom side of the glass plate, when the incident angle will be greater than the critical angle, then light will again goes back and it will hit the filter paper that is placed on the top of the glass plate. That's when again you will get a bright spot here and bright spot here. So here I have done only 2D figure, and that's why you will look like you will get a bright spot here, bright spot here. But if you consider a 3D figure, what you will get? You will get actually, if you connect this whole bright spot, it will get a circle. Eventually you will get a circle like this. You will get a circle like this. Then already it is written in the questions, and so this will be the maximum intensity, and then when scattered angle will increase, all the light will come back to the top of the plate, because if the light is, let's say, consider another ray, so this light will goes along this direction, it will hit, and you can see compared these two figure that this angle of incidence will be always greater than this critical angle. If this is the critical angle, then here is also the incident angle will be greater than critical angle. So this light will again return back to the glass plate, and then it will be hit on the top of the on the other side on the top, and it will hit the paper on the top, on the paper that is placed on the top. But as this scattering angle will increase, the intensity of scattered light will also decrease, and that's why the intensity of this bright circle will also reduce as we increase the radius. Okay, and the figure that is given in the questions, from there we can see that the radius of this circle is r. That's mean if we give a name, let's say this point is A, and then this point is B, and then this point is C. So this A to C, this will be the inner radius of the circle, that is R. And now if I draw a normal from this point. So this is a normal. So this angle will be 90 degree. And this is a critical angle theta c. So this is not just critical angle. It's assume that just greater than critical angle. So light will goes back in the second medium, and in this case this will also be the same angle. So this angle is just greater than theta c. So for thus calculations we can assume that it's a theta c. And let's say this normal touch this top surface at a point D. At a point D. And since this angle and this angle are equal, so we can say that D is the midpoint between A and C. So if AC is R, then AD will be R by 2. AD will be R by 2. If AD is R by 2, then from the triangle, right angle triangle, A, B, and D. So right angle triangle from A, B, D. What we can write? We can write tan theta C is equals to perpendicular upon base. So your perpendicular will be AD, that is R by 2, and base here, the thickness of this glass plate, that is D. Thickness of this glass plate is D. So from here we can write theta C is equals to tan inverse R by 2D. Tan inverse R by 2D. And then according to definition of critical angle that already we have learned in the previous page, of here we have written that theta c, the refractive index of any interface of two medium is sine inverse n2 by n1, where n2 is the refractive index and of rarer medium, n1 is the refractive index of denser medium. So if we use this definition here, so also we know sine theta c is equals to refractive index of second medium divided by rarer medium divided by refractive index of denser medium. So for this interface, rarer medium is here and denser medium is glass. So refractive index of rarer medium, that is air, divided by refractive index of glass. And now from here what we can write sine theta c is equals to refractive index of air divided by refractive index of glass. So air refractive index is 1, glass refractive index we have to find out, so we have to assume it is NC. So if we want to write NC, that is refractive index of glass, it will be 1 by sine theta c. 1 by sine theta c. And already from this figure we have calculated this value of theta c. So if we put it here, what we'll get? We will get this value of refractive index of this glass plate. NC is equals to sine and then tan inverse R by 2D whole inverse. So this is the refractive index of this glass plate. So I hope questions is understood. The main idea is you have to understood how this because of total internal reflections how this circle will form, and from there you can find out the critical angle from this geometry, and also you can another way you can also use the definitions of critical angle, and from there if we equate this to value of critical angle, finally we'll get the refractive index of this glass plate. Okay, so correct options will be option K. Okay, so thank you for watching this video. We'll see you in next video.